Hi everyone, my name is Javier Jimenez. I'm CCO of Herenguru, and today I'm going to show you our research on infrastructure optimization using agent-based modeling and Bayesian optimization. I would like to take a moment to tell you about the team that has been involved in this project. First, we have Mauricio Acuña, who has an extensive experience in the airline industry, working at LATAM Airlines in operational research in departments such as revenue management, pricing, distribution, loyalty programs, and more. Second, we have Mauricio Franco, who is our data scientist, and Mauricio comes from the academic world, and he recently joined our team to help us improve and implement the algorithms that you will see during this presentation. And then there's me, Javier Jimenez. I also have spent most of my career working in the airline industry, specializing more than all in revenue management and pricing, both on the operational research side as in the commercial team itself. I will start the presentation by describing how the ABM Simulator works. The ABM Simulator uses agent-based modeling to generate the simulation. This methodology is nothing new, but we have managed to scale it in a very efficient way using cloud computing. This methodology is very convenient for the type of simulation we want to do because it allows us to program different agents in the simulation. Each agent will have its own characteristics that ideally will have basic logic. And by interacting with the other agents in the simulation and with the environment, we will get these emerging effects, which would be things like load factor, revenue, yield, and other things. In our case, the agents program will be carriers, flights, and passengers, or to be more accurate, PNRs, because one PNR could involve 2 or more passengers. Our ABM simulator is built on the basis of comprehensive supply and demand models that emulate the most relevant commercial conditions. The supply model is fed with availability data, fare data, and schedule data. The demand model is fed with industry demand data such as IATA's TDS and with ticket information coming from the airline. Both models can be changed in any of their components to generate different scenarios for the airline to analyze and compare. After the model is prepared, we implement a two-step process. First, we calibrate the demand using Bayesian optimization, and second, we optimize any variable in the model using the same methodology. Today, we will show you how this two-step process can be used to optimize a fare structure. Let's take a deeper look into the agent-based model. As you can see, the model builds the agents in 3 steps. First, it loads the itineraries to generate the flight agents and also to pre-calculate all possible routings. Then it loads the RM and pricing strategies on the carrier's agents that will later interact with the flight agents to determine the final price the passenger will be given. And finally, the stochastic demand generators, which we will explain in detail in the next slide, produce the passengers that will interact with our model every day. The step function of our model is daily. This means that each day a set of passengers will try to fly to a destination within the model network, and each passenger will have its own preferences and its own willingness to pay. Based on each passenger's preferences and characteristics, each passenger will have an ideal itinerary. Then the model will calculate all possible options for that passenger based on the existing available flights and fares, and this utility model will penalize how far the itineraries offered are from the ideal itinerary for the passenger. And this will generate a perceived price. The passenger will pick the lowest perceived price, and if the willingness to pay of the passenger is higher than such perceived price, the passenger will book the flight. The stochastic demand generators allow us to build a realistic synthetic demand based on real-world data. We construct a stochastic demand generator by fitting the main characteristics that we have imprinted into each of our passengers or PNR models. You can see that each characteristic, such as willingness to pay, preferred number of stops, time of the day, advanced purchase, and others, are based on probabilistic distribution functions. The model will produce random passenger agents within the simulation following such distributions. This is very important because we can build multiple scenarios with the same demand characteristics, but not the exact same passengers producing such demand. This helps us to understand how robust a strategy can be if the particular agents change but the aggregated number for each demand segments remain the same. This model is very convenient as well to fit real-world data into the model, as we will see in the next slide. We build a demand model with a 4-step machine learning process that takes historic demand as an input. First, we cluster the demand using k-means clustering. For this step, we use the elbow method to determine the number of clusters we need for each demand group. Second, the algorithm fits each demand cluster's characteristics to a probabilistic function. The algorithm uses normal distribution, beta distribution, and uniform distribution depending on which shape fits better with the data's histogram. Third, the algorithm generates the stochastic demand generators using the fitted distribution functions. The demand produced at this point by the stochastic demand generators is based on constrained data. So, to unconstrain the demand, at the final step, we use Bayesian optimization to find how much we need to scale the willingness to pay and the demand levels of each stochastic demand generator to reach what unconstrained demand the model would need to produce results similar to the real-world data. The outcome of this process is a manageable demand compounded by multiple demand segments. Each of these segments can be molded in intensity or behavior to construct different scenarios. Decreases of 10% in demand or leisure demand shortening their average length of stay are some examples of scenarios that can be easily generated with the ABM Simulator demand model. Let me briefly show you how the Bayesian optimization works. Let's imagine we want to find the maximum point of an unknown function that we can measure in a limited set of points, putting as an input x and retrieving the result y with some noise. As you can see in these images, in the first iteration we have two samples of the curve, and the algorithm fits this into a prediction curve with a certain variance for each x input. The algorithm used these prediction curves to generate an acquisition function, which gives an indication of the next candidate that should be measured that will more likely, with the information we have until now, return the maximum point of the curve we are searching for. As the algorithm executes more iterations, it finds more information about the target curve, and the candidates offered by the acquisition functions will be closer to the maximum. When we reach iteration 10, the algorithm focuses more on testing points closer to the theoretical maximum of the target function, converging to the optimal point we are trying to find. There is the danger of falling into a local maximum if the exploration versus exploitation of the algorithm is not well controlled when using the acquisition function. In our case, we start the first iteration by incentivizing exploration, which means searching more random points in the search space independently of the initial acquisition function, and then in later iterations we'll gradually start focusing more on exploitation by testing candidates closer to what the acquisition function is suggesting. Now, let's review the network we have run using our simulator. This network has been constructed with real itinerary data and fare data, but we have hidden the airlines' names and we have sanitized the data. The model network is run with 4 airlines, 16 feeder airports, 4 connecting airports, 2 other airports that group smaller demand coming from less significant airports. We are running 40 simulations per iteration. 200 passengers per simulations are run. This amounts to 9.6 million per iteration. And each iteration is done in 45 minutes, thanks to a scalable infrastructure on the cloud. First, let's see how the demand calibration model worked using Bayesian optimization. In the calibration process, we will run 40 simulations, testing 2 variables that we wish to adjust in the simulations to transform our, quote, constrained demand, because it is based on constrained data, into unconstrained demand. These variables are a willingness to pay multiplier, which should be more than 1 because the passengers should always have an equal or higher willingness to pay of what she actually pays, and second, a demand multiplier that should also be more than 1 because we should think there is always demand that didn't fly for not having enough willingness to pay. If you take a look at the chart on the left, you can see the predicted function. In this chart, the z-axis represents the error, which we are trying to minimize. The x-axis is the demand multiplier, which is multiplied by 1000 for scaling reasons, and the willingness to pay is the y-axis, which is multiplied by 100 also for scaling reasons. Each red dot shown in this chart is one simulation run with a different set of parameters. It's easy to see how the algorithms end up focusing more simulations closer to what the predicted function indicates as the minimum. The optimal combination of demand multiplier and willingness to pay multiplier are 5.5 and 5.9. When we analyze the results, we see that the error reached when compared to our 1 month real-world data in both directions is 15.5%. Taking into account that this has been trained with pandemic data, this result is good but not great, and we can see why. Part of the problem is in the directions B to A, in which the weekly variance of the control month of the demand simulated is not aligned with the variance by week of the real-world data. Because we have not given the algorithm the degree of freedom to move week by week, the algorithm has no way to align the demand by week. We could improve this by giving more degrees of freedom to the model or by adding a causal variable that allows to adjust better the seasonality effect in the forecast of the model. We have chosen to stick with just 2 degrees of freedom in this experiment because we wanted to make sure we could reach convergence and also to easily see the results of the algorithm. Future work will aim to extend the search space because, as you can see, the optimal point is on the frontier of the current search space, and also to add more degrees of freedom, trying to maintain a good convergence. Now that we have calibrated the model, it's time to use it to find the optimal fare structure for the O&D A to B and B to A. In order to do so, we have run 2 similar scenarios. In one of them, we are assuming that the airline moves its fare structure and competitors don't follow. And in the next scenario, we have assumed that competitors follow every movement the airline makes. These 2 scenarios are very extreme, and we know that in reality, what probably happens is something in between. But they are very useful to analyze the contrast between these 2 situations. The method used to find the optimal fare structure is exactly the same as the method to calibrate the demand. The only difference is that now the acquisition function is the amount of revenue, and now we will program the model to find the maximum of the target function. And the other difference is that now we will keep the demand multiplier and the willingness to pay multiplier fixed in 5.5 and 5.9, which are the required multipliers to calibrate the model. And we will start looking in the search space with 2 other variables, the first step multiplier and the minimum fare multiplier. As you can see in this example, the minimum fare multiplier, or MFM, will multiply the minimum fare of the fare structure, while the first step multiplier, or FSM, will multiply the fare distance between each fare in the fare structure, making the fare structure longer by increasing the distance in price between each fare, or shorter by decreasing that distance. The size and complexity of the fares that will be handled by the model will be considerably higher than in the examples shown before. Each fare structure in this market has close to 1000 fares, and all of them have length of stay restrictions, advanced purchase restrictions, ticketing and sales date restrictions, and seasonalities and blackouts. In this animation, we can see the optimization model running for each iteration for the case in which competition does not make any pricing movement. We can observe how the algorithm adjusts the predicted function based on the points sampled on each iteration. We can also see that the algorithm first samples random points in the search space, but slowly starts converging into the maximum point indicated by the predicted function. If we take a look at the chart from a better angle, we can observe that the optimization algorithm has found a steep increase in revenue when the minimum fare multiplier goes below 1. This could be explained by the fact that the competition is not making any pricing movement, And under this scenario, the strategy to generate more revenue that the algorithm has found is just to undercut competition. Other, less obvious interesting thing that the algorithm has found is that it can generate more revenue if it increases the first step multiplier. This doesn't have the huge impact we see with the minimum fare multiplier, but still we can observe a clear increase in revenue thanks to the first step multiplier increase. The results of the optimization are pretty good. We can see that by reducing the minimum fare by 36.5% and by increasing the steps between fares by 33.8%, the simulation shows that an increase of 16.7% in revenues could be achieved. Let's remember that the chances a competitor doesn't make any movement when losing market share because of such an aggressive undercutting strategy are quite small. Now, let's take a look at our second scenario. In this scenario, we'll make all competitors follow the airline's pricing movements. The same as before, in this animation we can see how the algorithm starts sampling data to improve the prediction function. We immediately can observe that the predicted function is much smoother than before. This is because this time no undercutting is happening, and the optimal point will be more dependent on how the demand will react to the changes in prices. The result on this scenario is very interesting. The first thing we can observe is that in this scenario, the algorithm has found a completely different strategy. Here, the minimum fare multiplier has increased by 22.6% instead of decreasing. So if all competitors follow under this level of demand, the right move would be to increase the minimum price instead of reducing it. Another interesting thing we can see here is that the optimal solution for the first step multiplier remains the same, but not as aggressive as in the past scenario. We have found the optimal solution would be to increase the first steps by 28.4%. This strategy would generate 18.2% of extra revenue. It's very encouraging that the solution this method gives makes so much sense depending on the competitive scenarios that we have provided. And even though these two scenarios does not give us a clear answer on what to do with the minimum fare, and to understand that we will need to improve the competitor's behavior model in our simulator, we can see that the first step multiplier has always given the same answer, thus suggesting it would be a good idea to increase it regardless of the competitor's behavior. We need to stress that neither of these two scenarios are realistic, because in reality, airlines change prices based on a process that takes as input multiple variables, being only one of them the competitor's prices. Part of our future work is to implement more intelligent pricing strategies for competitors to generate more realistic scenarios. By looking at the detail on each scenario, we can observe that in the competitors do not follow scenario, the load factors are higher, as expected in an undercutting strategy. But we can also see the benefits of increasing the first steps between fares, which apparently is helping to improve the class mix on the higher classes. An hypothesis here is that the gating strategy was not well aligned to the fare structure at the beginning, and the fare structure Bayesian optimization found a way to align better the fare structure to the way the RM gating strategy was closing classes. If we then observe the competitors follow scenario, the load factors are lower than in the previous scenario, but we still see better load factors than in the base case scenario, supporting the hypothesis that the optimization managed to align better the fare structure to the gating strategy. We will need to do more testing to understand better how a fare structure optimization and a revenue management optimization working as separate processes could benefit each other. Let me share with you now our conclusions and also some of our next steps in this research. The ABM Simulator is a powerful tool that can be calibrated using real-world data, and then find optimal solutions by testing multiple scenarios at a very fast speed using the same method, Bayesian optimization. Future work in the ABM Simulator includes adding causal variables such as a holiday calendar or the GDP, and also more degrees of freedom to better calibrate and forecast the demand. Also understanding how a fare structure optimization interacts with a revenue management optimization model, If we discover there is mutual benefit, that could open an interesting line of investigation. We will work as well in improving the algorithm to optimize fare structures by using more advanced machine learning techniques. Experiment with extending the optimization model to other forms of pricing, such as dynamic or continuous pricing, is also within our plans. Thank you. If you would like to know more about Erenguru or the ABM Simulator, please contact me at javier@erenguru.com. Have a great day.